Okay, good afternoon. Welcome to the astronomy cycle department cycle of seminars, and thanks for joining us here, or if you're following us through YouTube. And today's speaker is Dr. Mike Rudick. So thanks, Mike, for accepting our invitation to be here today. And Mike got his PhD degree in physics at Caltech, and currently he's a CIERA postdoctoral fellow at Northwestern University. And in September this year, he will join Carnegie Observatories as a Hubble Fellow. Mike's works on theoretical and computational astrophysics in the fields of star formation and galaxy formation, and he's the leader of the Starforge project, that is a multi-institution initiative to develop cutting-edge computer simulations of star formation, and I'm sure he will give further details about this during his talk. So before we start, please turn off your microphones and cameras, and if you have a question, you can raise your digital hand here in Google Meet, or you can write it down in the YouTube chat, and the questions will be asked after the presentation. So Mike, whenever you are ready, you can start sharing your presentation.
Okay. All right, are the slides visible?
Yes.
Okay, excellent. Okay, thank you, Maria, for your kind introduction, and thank you everybody for coming. I'm very happy to be here and share with you this project that I am very excited about. So I will be telling you about the Starforge project, which is a multi-institution collaboration. So all of this work I've done here has been with the help of this list of collaborators shown here. So yeah, the way this talk is going to work is first I'm going to tell you a little bit about where simulations of giant molecular clouds and star formation are coming from and why they need to get better, what their limitations are. And this is the motivation for Starforge. Then I'm going to tell you about Starforge and how it actually works, how we actually do these simulations. And then I'm going to tell you some preliminary results from the first full physics Starforge simulations that we've run. So what I do is essentially try to understand how giant molecular clouds, clouds of gas between 10 to the 4 and 10 to the 7 solar masses, go from this gaseous state into stars and star clusters in galaxies. And we have some big questions about this process. We know the basic picture, the qualitative picture, which is that we start with this gas and we end up with stars, but we don't really understand any of the stuff that goes on in between. So among the big questions we have, we want to understand what the life cycle is for GMCs and star clusters. How do they form? How long do they live? And how does one transition into the other? We really want to understand the stellar initial mass function. So how many stars of different masses do you have? The stellar IMF is important for star formation and feedback. It's important for galaxy formation. It's important for practically any problem in astrophysics that you might want to look at. We want to understand star formation efficiency. So what fraction of the gas gets turned into stars and why? And does this vary from one place to another? Because star formation is typically observed to be a very slow process. It proceeds much more slowly than sort of naive intuition might have guessed. We want to understand stellar multiplicity. Why are some stars in binaries? Why are some stars not in binaries? Why are some in higher order multiples? And how high does this hierarchy go? And we want to understand star cluster formation. So why do stars form in a concentrated configuration? Do they all start in a concentrated configuration that eventually disperses, or do some remain? We want to understand that. So the answers to these questions lie in the physics of star formation. And the reason why we have sort of limited understanding of all of this is that there's a lot of different kinds of physics involved. You have to worry about gravity, turbulence, magnetic fields, chemistry, and stellar feedback. So by feedback, I mean all of the different ways in which stars influence the gas around them non-gravitationally. So that can include radiation, which can be powered by both accretion and nuclear fusion within stars. It can be with winds. It can be with supernova explosions that occur at the end of the lifetime of massive stars. And it can be in the form of protostellar jets and outflows that are launched when the stars accrete their mass. So my sort of first pass at this problem of star formation was with a large suite of simulations that I did during my time doing my PhD at Caltech. And this ran a wide parameter space of different kinds of giant molecular clouds following the way that they form stars and the way that as the stars form, they start to disrupt the GMC, as you can see on the left here. And eventually you sort of blow the whole GMC apart, limiting the amount of stars that you can actually form. So using these sorts of simulations, we've been able to say things about the effect of feedback on star formation efficiency. It appears that feedback is the crucial element that determines star formation efficiency. We were able to look at the way that star clusters assemble. We were able to make sense of the measurements of star formation efficiency in Milky Way GMCs. And we were able to construct a model that successfully reproduces the star cluster mass function in nearby galaxies. But I'm not here to convince you that I have all of the answers to all of the questions of star formation. I really want to know the limitations of any kind of simulation method that I use. So the big issue with the type of simulation that have been done thus far is that they aren't resolving individual stars. Instead, what you do is you have a piece of gas that turns into stars according to certain rules, and you make some assumptions about the stellar content of the stars that form and how fast those stars form. But you're not actually self-consistently resolving the star formation process. And I wanted to get some sense of how important one's assumptions about these prescriptions might be. So in this plot I'm showing here, I'm showing you the result of a GMC simulation where we run the same cloud with 5 different versions of these prescriptions. And we're plotting the total stellar mass as a function of time, as a fraction of the cloud mass. And depending on which prescription you use, or in turn, what you are assuming about how individual stars form on unresolved scales, your final result, your final star formation efficiency can vary by a factor of 3. So what that tells us is that GMC simulations that don't resolve individual stars are sensitive to star formation prescriptions. So that puts a fundamental limit on their predictive power because of all these different prescriptions, we don't know which one of these is actually the most realistic one. So essentially, this type of simulation can only tell you how massive a star cluster you form to within a factor of 3, and we want to do better than that. Now, historically, star formation simulations have been kind of divided into 2 regimes. So on the left, I'm showing you various examples of simulations that do resolve the formation of individual stars. These generally consider relatively small gas mass, less than 1,000 solar masses, compared to the million solar masses of a typical GMC. So we're looking at really a dense clump or a patch, a small patch within a GMC in these simulations on the left here. And they've included various kinds of feedback, including infrared radiation and protostellar jets. But they're really looking at just a small piece of the overall picture because the the resolution doesn't allow them to go to larger scales. So they're in a certain sense limited. Now on the right, we have simulations like the ones I did in the past that I just showed you, where you are simulating the entire giant molecular cloud, but the trade-off there is that you're giving up the ability to resolve individual stars and the IMF. And these sorts of simulations have been able to survey much larger masses. My simulations have looked at clouds up to 10 to the 9 solar masses, for instance. And they have incorporated stellar radiation, winds, and supernovae, but they can't resolve individual stars. And as I showed you, that is very limiting. Moreover, if you can't resolve individual stars, you can't really, there's no straightforward way to account for protostellar feedback. So feedback that arises from the accretion of individual stars, giving rise to jets like shown in these Cunningham simulations here. So both of these simulations on the left and the right on different scales have inherent limitations. And really what we'd like to have is the best of both worlds. So we want a simulation that can resolve individual stars and the IMF self-consistently, include all important feedback mechanisms, so radiation, winds, supernovae, and protostellar outflows, and can scale up to massive giant molecular clouds, which are responsible for most star formation. So that's the goal of the Starforge project. So the Starforge project is a new numerical framework implemented in the GIZMO code that combines all of the different kinds of physics that you might have to worry about in the star formation problem in giant molecular cloud simulations that can resolve individual star formation. So it combines magnetohydrodynamics, n-body dynamics, individual stellar formation and accretion, radiative transfer, supernovae, stellar winds, jets, and cooling and chemistry. So the backbone algorithm of Starforge simulations is the GIZMO code and its methods for meshless Lagrangian magnetohydrodynamics. So this MHD solver has numerous advantages for star formation problems. It has very good angular momentum conservation, which is important when you're following things over a large collapse factor and you want reliable dynamics and conservation. It is Lagrangian, so it follows around elements of a finite mass resolution, and essentially by setting that mass resolution, you can get some sense of what mass scale your simulation can resolve. So if we want to resolve the IMF, then we know that we need to set the mass resolution to something much smaller than the masses of stars. It also gets good resolution in shocks and overdensities because your resolution goes where your mass goes. It has straightforward and consistent coupling to gas self-gravity, which is again important because stars form out of gravitational collapse. It keeps the divergence constraint of the MHD equations very well satisfied to the point that its results are competitive with constrained transport codes that have zero divergence by construction. And particularly important advantage of this MHD method is that its time step is not constrained by the Eulerian cell crossing time. So if your simulation uses a fixed grid, then those grid cells can't take a time step longer than their size delta x divided by the bulk velocity. In other words, the crossing time, and that's the famous Courant condition. But because the cells move with the flow of the gas, we actually have to satisfy only a much weaker Galilean invariant time step constraint. And this actually makes the simulations much faster when you have very fast bulk flows with jets and winds and disks. It's also less diffusive in the supersonic flows that stars form in because AMR codes tend to sort of turn structures into mush as they get advected across the grid. at supersonic speed, and this is well documented in galaxy simulations. Another thing that helps make the Starforge simulations possible is the optimizations we've done to the gravity solver. So we've come up with a new scheme where the gas cells no longer have to call the gravity solver every single time they take a time step. Instead, what they do is they wait until they actually need a new gravity force. And in between those updates, they use an interpolation scheme. And the reason for this is that the time scale or time stepping for many of these gas cells can be much shorter than the gravitational time scale. And it's the gravitational time scale that sets the frequency with which we need to update the gravity force. So here I'm showing you the results from the paper about this gravity hack. And I'm showing you two different GMC simulations. So starting from the same initial condition, the one on the left uses this gravity optimization. The one on the right does not. And you can see that they look essentially identical, but the difference is that the one on the left evaluated 10 times fewer gravity forces, and that gave it an overall speed up of 2.1. So the simulations can run considerably faster thanks to this optimization. Now, we're following individual stars, and these individual stars can have close interactions and they can form binaries. And we're interested in binaries, and we don't want the binaries' properties to be contaminated by numerical effects. So that means we need some control on the accuracy of the numerical integration of binaries in particular. So here I'm showing you the energy error per orbit for various different types of numerical integrators for an eccentricity 0.9 binary. Shown in black here is the sort of standard second order integrator used in GIZMO and many other multi-physics codes. And it converges at second order. So this parameter eta here parameterizes the time step size. So essentially what this means is that if we want to get relative energy error per orbit that is small enough for our simulations, we have to go to very small time steps with this second order integrator. So what we did is we came up with a new fourth order Hermite integrator, which is actually a completely new integration scheme that is particularly efficient for the way GIZMO does time stepping. And at fixed time step size, it is orders of magnitude more accurate than the standard second order scheme. And what this means is that we can follow binaries for millions and millions of orbits, which we have to do because the lifetime of the GMC is on the order of 10 megayears. So if you have a 100-year binary, you need, to be able to follow it faithfully for at least 100,000 orbits. So to follow individual stars in the simulation, we have a sync particle algorithm. So essentially what that is once a Lagrangian gas cell satisfies certain rules, it can turn from a gas cell into a sync particle. And the sync particle can accrete other gas cells, which each have a certain finite mass resolution, delta M as shown here. And once a gas cell is accreted, its mass is transferred to the sync particle, and the gas cell is deleted. And the mass goes into a sort of accretion reservoir, where a fraction of the mass that goes into this reservoir goes straight onto the star. The stuff that doesn't go straight onto the star goes into the jet reservoir. And when there's enough mass for a jet feedback event, then feedback is injected in the form of protostellar jets. Meanwhile, the star is continually transferring mass to the internal wind reservoir of the sync particle. And again, when the wind reservoir reaches a certain minimum mass, you will have a stellar wind injection feedback event. So for coupling feedback, we have two different ways to model the way stars inject mass, energy, momentum, and photons into their surroundings. So the first is what we call local injection. And this is essentially just where the star searches for a certain number of surrounding gas cells, and it injects the conserved quantity into those surrounding gas cells according to a certain weighting. And the specific weighting we use is essentially the same as is assumed in the magnetohydrodynamic solver. So we construct effective face areas between the star and the different gas cells according to a certain volume partitioning scheme, and we weight the injection according to those face areas. The other method for injecting feedback is where we create new gas cells. So this is where we're injecting mass and we simply create these new parcels of mass in the simulation. And this is done in a way where these mass parcels are injected with antipodal velocities and positions with respect to the star, so it conserves the center of mass and momentum to machine precision. And this is important where we're in a diffuse region like a wind bubble or a jet cavity, and we might not be able to find enough gas cells in the vicinity of the star to be able to do this local injection. So instead, we just create new resolution elements and inject those. So the protostellar jets are handled via the cell spawning technique, where we actually let the masses of the jet cells be a factor of 10 finer than the standard mass resolution of the cells in the simulation. And these are arguably the most important feedback mechanism for low to intermediate mass star formation. So they regulate stellar accretion by sort of entraining gas away from the star as it accretes. I'll show that to you again. So stuff is falling onto the star, but as the jet gets going, this mass is transported away. And that's been shown to greatly reduce the mass that a star can actually accrete, which regulates the IMF. And we use a simple parameterized phenomenological model from Cunningham 2011 to decide how much mass and momentum is in these jets. We account for stellar radiation in 5 different frequency bands. So we have hydrogen ionizing or Lyman continuum photons. We have photoelectric photons. We have near UV photons, which actually carry most of the momentum from a stellar population for radiation pressure. We have optical to near IR photons, which can be important because they have lower opacity than NUV, so they can couple on larger scales. And we have far to mid IR, which is important for setting the thermodynamic state of the gas when it's affected by dust heating. And also it can exert significant radiation pressure in very dense protostellar envelopes. And we solved the radiative transfer equation using GIZMO's M1 radiation solver, which essentially closes the radiative transfer equation with at first order. So we're following a set of hyperbolic equations that kind of transport photons around simulation in a similar way to affecting gas around according to the continuity equation. We account for stellar winds, which are dominated by contributions from OB stars and Wolf-Rayet stars. And we follow a simple phenomenological prescription because wind mass loss rates are highly uncertain. So essentially, we just use a simple prescription that seems to reproduce observed mass loss rates. And for this, we use an adaptive hybrid method. So if a free expansion radius of the wind is currently resolvable, then we just directly inject the gas cells that make up the wind. However, there will be instances where the free expansion radius cannot be resolved, and in that regime, it's not helpful to do the cell spawning, so instead we do the local injection. because essentially if you spawn the cells, then they'll just immediately collide with something and thermalize, and you get the same results. Lastly, we account for supernovae. So at the end of their lifetime, stars in our simulations greater than 8 solar masses undergo a 10 to the 51 erg explosion, and we simply spawn the supernova ejecta and evolve it directly through all the different phases of the explosion, from free expansion through the Sedon-Taylor phase through the snowplow phase. So without further ado, we have all of these different elements that we're putting together in the simulation. So we put it all together and see what we get. So here we have a 20,000 solar mass giant molecular cloud in a simulation that includes all of the different Starforge physics. And I'll show you what we get. So we start this cloud with some initial turbulent motions, which seed dense regions within the molecular cloud, some of which become self-gravitating and go on to form stars, some of which you can start to see now. And you can see that some of these stars are accreting rapidly and growing and emitting protostellar jets. And as I mentioned, this is a very important process for regulating the IMF and star formation. And as the cloud reaches a more and more advanced state of collapse, you get more and more stars forming. And we've got some massive stars over here that have started to blow out their surroundings with their ionized radiation in these H2 regions. And you can see that we're in this kind of complicated sort of fractal clustered distribution of stars right now. But as the cloud collapses, the stars kind of assemble into a central star cluster, and the stellar substructure starts to get erased. And at the end of the simulation, the cloud is essentially completely disrupted and star formation has ceased. So we are actually able to measure the final stellar mass and the final IMF and all of these interesting things from the simulation. So first question is star formation efficiency. So the simplest question we can ask is just what fraction of the initial gas mass actually gets converted to stars? In black, I'm showing you the fraction of gas mass converted to stars as a function of time, and you can see that it kind of rises, and it's very, very dynamic. It's not a linear relation, but rather it scales steeply at early times. But it levels off when the cloud is disrupted, and we end up converting about 7% of the mass of this cloud into stars, as shown by this dashed line here. Now, you can't actually directly measure star formation efficiency in this sense. You can only infer it indirectly, but the value that we get is in good agreement with what was inferred by Chavant's 2020, who applied a statistical model to data from nearby star-forming galaxies. And these other curves I'm showing you in the orange and the green, these are mock observations of different proxies for star formation efficiency that people use. So in green, we infer stellar mass from the free emission coming from H2 regions. And in orange, we infer stellar mass from the number of young stellar objects that would be observed. And we see that either of these mock observed star formation efficiencies do spend most of their time in the observed range. So in other words, no matter how you cut it, these simulations do appear to be reproducing the observations of star formation efficiency pretty well. Moreover, we can see how these different metrics for star formation efficiency are kind of biased. So the young stellar objects estimator overestimates the stellar mass at early times and underestimates it at late times, while the free emission one has the opposite problem. It underestimates at early times and overestimates at late times. This is because if you're simply counting the number of young stellar objects, well, you have to multiply that by an average stellar mass to get stellar mass. And this average stellar mass is actually small at early times and large at late times, because as we'll see later, low mass stars seem to form earlier than high mass stars. Meanwhile, this free emission metric is insensitive to the early stages of star formation because there are simply no massive stars around to create H2 regions and free emission. Meanwhile, at late times, we're starting to destroy the molecular gas that would be used to observe the star forming region. So the gas mass that is observed goes to zero, and this shoots off to a large value. And all of these same sorts of findings apply equally well to the star formation efficiency per free fall time, which is another thing people measure. So again, we have these different biases for these different observational tracers, but the simulation spends most of its time in the observed interval. So another thing we can look at is the relation between the star formation rate and the mass in dense gas. So by dense gas, I mean, according to the definition of LADA 2010, which is gas with a K-band extinction of greater than 0.8 magnitudes. And what we find is that the simulation does appear to spend most of its time in the regime observed in nearby star-forming regions within the Milky Way. So it appears to reproduce that pretty well. There is some question of why we don't observe things in the lower half of this plane, which we do find in the simulation. And that may suggest some sort of picture where the dense gas mass is sort of created in concert with star formation, as opposed to just starting with the dense gas mass and then the stars come later. So this may yet provide some constraint on the star formation process. Another interesting thing to look at is how long stars of different masses take to form. So here we're looking at just that. On the x-axis, we have the final stellar mass that a star has. And on the y-axis, we have the time that the star takes to accrete 99% of its mass after its initial seed forms. And what we find is that the average value is actually in quite good agreement with the observationally inferred about 300,000 years, but that it can vary considerably from star to star. And in particular, we seem to have this trend where the time it takes for a star to form scales to the 0.4 power of its mass. So what that means is that stars of greater mass tend to take longer to form on average. And what that means in turn is that early times in star formation will be biased toward having or bottom heavy mass function, and the full mass function won't emerge until later in the cloud's lifetime when all of these stars have had time to accrete all of their mass. And this can have important implications if you want to actually model feedback, because you have to account for the way the massive stars come later, and also modeling stellar populations for unresolved photometry. If you want to know the mass of your star cluster, well, at early times, the massive stars are essentially absent. So you can have actually a much greater stellar mass than you would infer from simply randomly sampling from the IMF if you want to infer cluster mass from photometry in another galaxy. So this is very interesting, I think. We can also look at the IMF, and what we find shown here is that the IMF does have a shape that resembles the observed IMF. So I show you sort of three different flavors of standard IMFs here. And it does appear that the sort of peak mass is in the right place. On the left here, we have a sort of well-documented incompleteness due to the finite resolution of the simulations. But the interesting difference here is that the IMF we get is slightly less shallow than the observed IMF. So we get a slope of about -2 or -1 on this log histogram plot. And the typical value measured is more like -2.3 to -2.5. So in other words, we have slightly too many massive stars. And that's interesting. It might be telling us something about what we might be leaving out of the simulations, or perhaps what kind of initial conditions we should be using. However, I still consider this a win because the version of this simulation that had only protostellar jet feedback had a maximum stellar mass of 300 solar masses, and that is completely absent from this simulation. The most massive star we got here is only 55 solar masses. So what that means is that these additional feedback mechanisms, radiation and winds, drive bubbles that stop massive stars from growing. So we successfully get rid of these overly massive stars, but we're still a bit top heavy, so perhaps there's some interesting physics explanation for that. We can also look at multiplicity, and you should focus here on what's shown in orange, which is the multiplicity fraction. So the fraction of stars of different masses in multiples. And we reproduce observations fairly well, modulo the uncertainties of both the observations themselves and mock observing the observations, where most stars of low mass are not in multiples, while most stars of high mass, or practically all above 10 solar masses, are in binaries or multiples. So that looks pretty realistic. We've also done simulations at much higher resolution than the one I showed you. And these simulations are high enough resolution to resolve the disks around young accreting protostars. And we have a bit of an interesting puzzle here because on the left, I'm showing you what we get without magnetic fields. And we get these very rich, ubiquitous disks around every star that forms. And on the right, I'm showing you what happens when we turn on the magnetic field. On the same color scale, there's basically very little gas and no disk around the stars. The gas is falling straight in. So this is what's called in the field a breaking catastrophe. So magnetic torques simply allow gas to fall straight onto the star, and you have no real disk to speak of. So this is an interesting puzzle, and we're interested in figuring out what's going on here and what you need to do to get disks around these stars while still having the magnetic field. So finally, I'm just going to tell you a few things about where we're going with this project. And I think the biggest question we want to address is the IMF. So we want to know if the IMF depends on GMC properties, metallicity, radiation field, redshift, or galaxy type. So we're running a huge parameter survey covering all of these different things to see how the IMF responds to these variations. We want to know what observational biases might exist when we try to measure the IMF. So we want to use the simulations to interpret observations. And perhaps we can say something about biases due to missing runaway stars or having mistaken cluster membership, or a simple time dependence in the IMF since massive stars take longer to form. We'd also like to understand what is the minimal physics explanation for the shape of the IMF. So our long-term goal is to take our findings from these simulations, use them to narrow down what is relevant and what is not relevant, and develop an actual theory of the IMF. I also want to apply this to galaxy formation simulations. So galaxy simulations have no hope of resolving individual stars, so they have to use these prescriptions. And nobody has ever explicitly validated one of these prescriptions against star formation simulations that resolve the IMF, because there's been no overlap between the mass scale you can simulate in a galaxy simulation and the mass scale you can simulate in one of these GMC simulations, but now there is. So the issue is the state-of-the-art prescriptions are calibrated to these older star formation simulations that don't get the right IMF, so they're not really simulating star formation as observed. Moreover, the choice of prescription for star formation in galaxy simulation matters for the properties of giant molecular clouds and star clusters. So that means that if we want galaxy simulations to extend their predictive power down to the scale of GMCs and star clusters, we need more advanced star formation prescriptions. And we're going to use Starforge to actually provide a sort of reference that we can tune a star formation prescription to reproduce. And the advantage here is that it actually does get a realistic IMF. It does get a realistic star formation efficiency. So it's a more reliable model for calibration. So we'll be able to validate or refute all of the different star formation prescriptions people use by simulating exactly the same GMC at galaxy simulation resolution and at our Starforge resolution, which we can do now because we can do these massive GMCs. And lastly, we're hoping to scale up Starforge to galactic scales. So we'd like to do a sort of slab of galaxy, a couple hundred parsecs on the side, as shown on the right here, with maybe 10 to the 7 solar masses in gas in it. And this would be nice because then we don't have to assume initial conditions for our GMCs. They simply form self-consistently, and we can make a more realistic model. And it's even possible that we will be able to simulate ultra-faint dwarf galaxies with individual stars with the appropriate refinement scheme in a cosmological simulation. So to summarize, Starforge makes it now possible to simulate massive giant molecular clouds while predicting the IMF self-consistently with all of the different important feedback mechanisms. And we've built the laboratory essentially, and now it's time to do the experiments. So we're ready to tackle the big problems of star formation, like the IMF, multiplicity, star clustering, and star formation efficiency. It seems to be looking pretty good for star formation efficiency, multiplicity, and preventing the formation of unrealistically massive stars. But our IMF is a little bit top-heavy. It's a little bit too shallow, which hints that maybe there's some sort of missing physics. And we're also missing disks around our stars when we go to the resolution needed to resolve these disks. So there may be some kind of MHD physics that we're leaving out that is important for having protostellar disks. And lastly, I'd like to emphasize that this has many applications outside of star formation theory for its own sake. And we're looking forward to applying our results to galaxy formation simulations and eventually making predictions on cosmological scales. And with that, I'd like to thank you for your attention and end the talk. Thank you.
Okay, thanks. Many thanks for this great presentation. Well, awesome results. I will break the ice with my one question, and then I will follow with the other questions. I have a question concerning the initial conditions. Like you start with a spherical ball of gas with the turbulence, I guess, right? How do you choose these parameters for your initial condition?
Right. So yeah, the initial conditions we've tried so far are fairly contrived and simplistic. So they're, as shown here, just a uniform density sphere, and we simply sample a Gaussian random field for the initial velocity with a certain prescribed power spectrum to match what's observed in giant molecular clouds. And we also simply give it a uniform magnetic field. And we set the mass and size of the GMC to lie along the size-mass relation of GMCs in our galaxy. So yeah, that's what we do. And I actually have a student working on something a little bit more realistic, where essentially what we do is we first sort of do something like shown here, where we run a simulation where we drive some initial stirring of turbulence and allow the substructures and velocity and magnetic field correlations to arise self-consistently. So we'll be putting out a paper soon where we show what we get when we actually do this new kind of initial condition. It turns out initial conditions don't actually matter that much, so much as whether or not you continue to drive the turbulence. In other words, modeling injection of energy from larger scales.
Mm-hmm. Great. Okay, I will just let other people ask. Juan, you can ask your question.
Hello, thank you very much for your very nice presentation. Can you hear me? Oh, you cannot hear me, right?
I just lost
I
you,
can.
but I hear you now.
It's fine.
Okay.
Okay. So my question was regarding you mentioned that one of your goals is to model the initial mass function, and you mentioned that perhaps there's some physics missing. I was wondering if regarding feedback, cosmic ray pressure could be considered as one of these components about missing physics, or is in your community there is a reason to completely neglect cosmic ray pressure as a feedback component? This is one question. I have another one.
Okay, so yeah, I'll first answer the question regarding cosmic rays. So yeah, cosmic rays have gotten a lot of attention in the galaxy formation community in recent years, because it does appear that if they have the right transport coefficients, then cosmic ray pressure can be very dynamically important on the scale of galactic halos and sort of down to the galactic scale height. But the issue with cosmic ray pressure in GMCs is that if you're in such dense gas, then you just have such catastrophic losses to cooling that you can't really build up a large enough amount of cosmic ray pressure to affect the GMC dynamically. So this is based upon mainly the findings of these various galaxy simulations that resolve the IMF, like by Phil Hopkins. We seem to find that the cosmic ray pressure doesn't do much within the GMCs themselves, even though it can be important on galactic scales. So that's probably not the solution here. However, the cosmic rays can still be an important source of ionization, which in turn can affect the cooling and chemistry and the coupling to the magnetic field. So they may be important in that regard.
Oh, thank you. The other question is related to how universal is the initial mass function. So perhaps, well, the model that you predict is perhaps correct, but the observation is not suitable, or your model is not suitable for the observed data. I mean, if the initial mass function is universal, or do you expect also some variations to this observed?
Yeah, so I think we are seeing some hints of IMF variations in our parameter survey that we're running right now. However, they are fairly small to the point that I'm not sure whether the observations would even be able to pick them up. So we are seeing, I'll just give you a sneak peek, we are seeing a slightly more top-heavy IMF in low metallicity conditions. Not by much, but enough to affect the number of supernova progenitors by a factor of 2 or 3. So that's possibly the most interesting result that we seem to be getting right now. But interestingly enough, if we varied simply the surface density of the GMCs by orders of magnitude, and over a factor of 10 to the 3 in surface density, we seem to get the same IMF, more or less. So it appears some variables do change the IMF and some do not. And there's an upcoming paper by my collaborator, David Busenov, which will present all of these different results.
No, thank you.
Okay, Reinaldo, you can ask your question.
Thanks, Mike, for the presentation. It's really incredible, this code. I think in terms of efficiency, it's really astonishing. I have first one comment about the disk, the problem of the missing disk. Well, I would guess that the problem there is that maybe at these scales, maybe the hydrodynamics phenomena like turbulence, and maybe also the microphysics like resistivity at viscosity. Maybe the resolution is not enough to achieve these scales, although you can simulate very well the laminar phenomena, maybe turbulent phenomena, you cannot reach these scales. Maybe it's one suggestion to test what's the Reynolds number at these scales, maybe calculating the structure function. You can find the scale of where the numerical effects starts to dissipate too much, the motions. It's just a guess. Maybe you can comment about this. And I have another question for larger scales. If, well, when you start to have a feedback from the objects, does the turbulence generated by these objects, by this feedback, is more important than the turbulence you are, I don't know if you are forcing turbulence all the time, or you just put one initial turbulence and it decays. My question is, what's the evolution of this turbulence? It becomes more important, the contribution from the outflows?
Okay, so yeah, thank you. So for your first question was regarding whether the issue with the disks might just be that we're not resolving the relevant scales of turbulence. And that is possible. I can say that across a fairly large baseline in mass resolution from 10 to the -4 to 10 to the -6 solar masses, we observe no trend with resolution in the disk properties in the hydrodynamic simulations, but all of the MHD simulations lack the presence of disks. I think a more likely thing is just that you touched on it a bit. So there's resistivity, there's non-ideal MHD effects, and these are not accounted for in our present simulations. So these can easily lead to a situation where the gas simply decouples from the magnetic field, and its angular momentum transfer becomes much less efficient. And there have been various works with adaptive mesh refinement simulations showing that this might work. So that's probably the direction we're going to head in with this. Now, regarding the driving of turbulence by feedback, so yeah, feedback is very important for the global kinematic state of the cloud. And the way it works, of course, depends upon the type of feedback. So it seems that protostellar jets, while they moderate the rate of star formation and individual stellar accretion, they don't really do very much to the overall turbulent cascade, except you get a sort of small excess in power on small scales. But they don't seem to affect the global eddies within the cloud. Whereas, as you're kind of seeing in this movie here, these expanding H2 regions, they do affect the cloud kinematics on the global scale. And in fact, if you run the simulation to the end, they simply completely destroy the cloud. Now, it's, I guess, sort of academic whether this is can really be understood as a turbulence effect or as more of a coherent flow effect, and we're not really sure of that right now, but we're analyzing the kinematics of simulations to try and answer these sorts of questions. But yeah, essentially feedback eventually destroys the cloud altogether, so it is very important for the overall kinematics.
Thanks. Does the, sorry, a very last question. Does the IMF depend on the parameters of the turbulence you choose to inject? How the degree of the Mach number or something like this?
Our results on that are still preliminary, but they hint that the details of turbulence are not so important for the IMF. We've run simulations with purely solenoidal motions and purely compressive motions, and they get very similar looking IMFs. We've also run simulations across a wide range of Mach numbers, again, very similar IMFs. So it appears that the IMF has a certain robustness to the properties of turbulence.
Thanks a lot.
Thank you.
So Betty, you can ask your question.
Oh, hi. Thanks for the talk. I have another comment with regard to the magnetic catastrophe in the transport of magnetic fields to the
I can't hear you right now. I'll let you know.
Betty,
I can.
I think your connection.
Yeah, I hear you again.
Oh, it's irregular. So
Yes.
I hear you now.
oh, okay. So we can you hear me?
Yes, I can right now. Yeah, I'll let you know if it cuts out again.
Okay. No, yeah. So my comment is that really the missing physics here may be the process that allows for the transport of the magnetic field to the outskirts, right, in order to avoid the magnetic catastrophe. And that, as you know, the ways to avoid this are, for instance, ambipolar diffusion. It's one of the candidates. However, there are still open issues with the efficiency of ambipolar diffusion at those scales. And the other possibility is as Reynaldo has before me has pointed out, is turbulence itself. So turbulence and magnetic reconnection, fast magnetic reconnection driven by turbulence can provide this diffusion, right? And actually, we have tested this by means of the MAGD simulations, ideal MAGD simulations, but with the turbulence. And we could check that with the presence of turbulence in the forming, in the collapsing disk, the turbulence has the means to transport diffusively by reconnection diffusion the magnetic fields to the outskirts, or part of the magnetic field to the outskirts, to the envelope of the collapsing star, and allows for the formation of the protostellar disk in a similar way to the pure hydro case. So this, of course, it depends on the presence of turbulence and maintenance of the turbulence at these stages, and this is an open issue. But this may be, the missing physics, a key point, a key missing point in these simulations, in these models. And the other, this is a comment, but I do have a question regarding your simulations of galaxies. When you have this inner region, what is the scale that you showed very quickly? Yes, yes, this simulation. So what is the IMF and the star formation rate that you use? It's a starburst like ingredient or normal regular star formation, as in a regular galaxy like ours, I mean the Milky Way. And what is the so you have, this is within 200 parsec region, right? 400 parsec in diameter, right? So it's the inner scales. So essentially, what is the star formation rate that you apply in this case, and in order to see this feedback and the formation of this wind?
Right. So I should emphasize that this is a type of calculation that we are planning to do and have not yet done. But the idea here is to simply start with an environment similar to the solar neighborhood. So you have a gas surface density of about 10 solar masses per parsec, and you consider maybe a box 300 parsecs on a side. And the idea here is not to prescribe any kind of star formation rates, but rather treat it as a numerical experiment to follow star formation self-consistently.
Right.
So that's the idea here, but yeah, we haven't done these yet.
Right.
We're hoping to.
Right. Okay. But how do you intend at these scales to follow and to obtain the star formation rate from first principles?
The idea is still to simply follow individual accreting sync particles.
Right.
Now, at the resolution attainable in this sort of setup right now, you can't resolve the whole IMF, but you can still actually predict the sort of part of the IMF where most of the mass is and get the number of massive stars more or less right. So that in turn will mean that the feedback will come out okay. But yeah, the idea here is simply to scale these GMC simulations up to these to simulate a whole patch of galaxy.
Right. Interesting. Okay, thank you.
Thank you.
Okay, so let's finish with Reinaldo's question. I think your microphone is muted.
Sorry, I'll make a question. I guess a lot of people make this question when you presented this work about the development you are doing with this technological development with the algorithms. So in your group, is there any plan to expand this to other problems or these ingredients that maybe appears in other problems in astrophysics, in, let's say, AGN, is maybe to make it public in the future, these models? Or
yeah, so actually much of the numerical machinery in Starforge is already available in the public version of the GIZMO code, including all sync particle formation and accretion algorithms, which can actually be applied to things like AGN accretion or other problems. Yeah, there's also a lot of stuff we've sort of worked out for Starforge that can be useful in other sorts of problems, like adding this high order integrator to the code, which might be useful if you want to do planetary systems with hydro or something like that. So yes, there are many applications of the algorithms we've developed to make Starforge possible. And for the most part, they are actually, all of these different algorithms actually are in the GIZMO code. And more will be added as time goes on.
That's great. Thank you.
Okay, we thanks you again. Many thanks for your extraordinary talk. And well, Richard, we can. I want also to thank the people that are joining us in YouTube. And Richard, whenever you can, we can stop the transmission.
Thank you so much, everyone. You've been wonderful.
Thank you.
All right. I'd love to stay in chat, but I actually have to get to a meeting now. So yeah, thank you so much, and I hope to see you again soon. Bye.
Thank you, and yes, hope we meet in person someday.